Dr. Robin Humble has a PhD in computational astrophysics and a previous career worked on planet formation at the University of Toronto. He's been building clusters since 1998 and top 50 machines since 2003, and he's currently the system analyst for NCI National Facility in Canberra, Australia. Ladies and gentlemen, Robin Humble.
Thank you. So this talk was billed as being about root on Lustre, but I'm actually going to try and minimize that part of the talk, and the second part of the talk will be mostly about speeding up metadata, which I think will be of more use to a lot of people here. So as we haven't been to LUG before, I thought I'd give you guys a one-page background about our site. So my name's Robin Humble. Thanks, Dave. And David Singleton from NCI is also here. Together we work on most of the operating system file system issues on our site, and also David writes our PBS. So there's a very brief background. We've been around for quite a long time. My current machine is about 12,000 fast Nehalem cores, 1,500 nodes, about a petabyte of disk, 26 OSSs. So it's not big by any means on the scale of some people's machines here, but it's not small either. Some things that make our site a little bit interesting is that we run a very wide job mix. So we intermingle single core 600-hour, usually computational chemistry jobs, with 8,000 core debugging runs for turbulent combustion. So the way we can effectively do this is because we have a suspend resume scheduler. So this is basically to sig stop, sig cont, and it means that an 8,000 core job that's 2/3 of the machine only wants to run for 20 minutes. It might spend 10 minutes in the queue waiting to start. And it's just it's sort of, in our mind, it's a far superior model to that of backfill schedulers. So we not only get good machine utilization by using suspend resume scheduling, but we also get good interactivity for debugging jobs, large debugging jobs in the queue. So I guess another slightly odd thing that we do is we set load run path, a kind of obscure variable, in all of our module files, so that any module file that involves linking to a library. So the idea behind this is that we can aggressively update the latest version of things like OpenMPI and compilers, and we don't break any old executables. They all still link against the libraries they're originally built against. It's kind of like static linking, except not. The other odd thing we do is root on Lustre. So let's dive straight into that. First, a bit of an overview about how we manage the clusters. So we've got a set of management nodes. These have got no Lustre involved. They're strictly boot off their own local RAID disks. But we really only have one OS image that's just arsynced from one master management node to the rest. So we really just have one management node image. And in one of these management nodes, we have the master copy of the operating system images for our compute nodes and for all our Lustre servers as well. So the compute nodes run with root on Lustre, and I'll talk about them in the following slides. The Lustre servers actually boot very much the same way as all of the compute nodes do, except they async their image and put it in a RAM disk. So we have OSSs and MDSs completely running out of RAM disk. Well, they use swap on local disk. So root on Lustre, why would you do something like this? The main reason is that there's a fewer software components that can fail. It's also cute and elegant and all that sort of thing, but we're really doing it because it's practical. We don't have to worry about how IP over IB behaves under pressure if we were using NFS. We don't have to worry about local disks in nodes dying if we were using the OS on local disks. And we don't have to worry about all the vast memory use of putting a whole OS in a RAM disk on a compute node. So we've got all this expensive, centralized, reliable, rated hardware that we use for our big Lustre file system. If that big file system is down, then all our jobs are hung. So our rationale is that we may as well put the operating system on there. If we're going to bet the farm on Lustre, we may as well bet the whole farm. So maintainability is another point. So if we want to update the package in our operating system image, we just cheroot into the directory on one of the management nodes, alter that OS image, get out of the cheroot, then we do one rsync that sends the copy of the operating system to the live running root file system on Lustre, and instantly with one rsync every compute node is updated, and that works flawlessly. So read on Lustre, how do we do it? Well, we use OneSys, provisioning system originally out of Sandia, I think. And I guess the light speed introduction to how OneSys works is that you send a kernel and a custom init RAMFS that OneSys makes for you, send that over the network to a compute node. Inside the init RAMFS is a bunch of network modules that OneSys loads. It then figures out where it lives in the network, sets up its network, mounts the root file system, cheroots into that, or switch roots into that, and then there's another part of OneSys that lives in the operating system, and that configures each node's separate identity using another tiny RAM disk full of symlinks and small files. We really like it. It's a simple and elegant thing, and it turns out to be easy to hack too. So basically what we've added to OneSys is we've extended the common OneSys usage case of read-only root on NFS, which is used on modest-sized clusters, and we've extended it to understand Lustre, and to be able to do read-only root on Lustre as well as read-only root on NFS. We got a laser pointer actually, or something like that? Oh, okay. So how do we actually boot a compute node? We have this Lustre root argument that we give on the Pixie command line. So this turns up on the kernel command line, and the init script from OneSys passes this script. So the first part of there is just a typical Lustre mount line. So you got your MGS, your fabric, your failover MGS, and the Lustre file system. Oh, thank you. So the first part of this is just a standard Lustre mount line. And the second part of this is a directory which lives in this images file system in this case. Excuse me. And this is just the directory where the root of the operating system copy that lives on Lustre lives. So that's the live operating system that lives on Lustre. So we just extended OneSys to load up InfiniBand modules, make sure the fabric is stable, load up the Lustre modules, do a mount Lustre, and then switch root into it exactly like you would for root on NFS. I won't really go into all the details of all of the hacking around with the init RAMFS that you had to do this, but you can just have a look at this wiki page, and it's a work in progress. I only made it at the conference 2 days ago, but it should give you an idea of what's going on. So, okay, that's really the end of the talk. It kind of works fine. Did anybody think it wouldn't? Of course it just works. Lustre just works. So, strange things that I guess we've encountered. This first one is a strange thing. It turns out that if you mount a file system in the future and then your metadata server reboots or crashes, then the node that mounted that file system doesn't work anymore. So I never really paid attention to what time the BIOS gave the compute nodes, but it's actually important when you're mounting, when the BIOS doesn't understand time zones, it's set in local time. We happen to be 11 hours ahead of UTC in Australia, and then you get into the init RAMFS, it doesn't understand time zones either and assumes it's UTC, and so it mounts the file system. In the future, the OS comes up, slews that time to the correct time, and then if the MDS reboots, your node crashes. So it's a really simple workaround that you just give an extra kernel command line option of time shift 12 or time shift 24, however many hours you want, and so you slew the time back inside the init RAMFS before you mount the Lustre root file system, and this gets you out of this failure case, and you can survive metadata server reboots at any time. So the second point here is really just a tweak that we added to pure Lustre root. I call it a half root. It's kind of the hybrid mode. And in this mode, we put the root of the file system and a few small directories into just a local RAM disk on every node. We actually did this initially because we thought it worked around this MDS reboot problem, and it turned out it didn't. But we actually, and we've been running for most of our 3 years of production use with root on Lustre with this half root mode. We recently switched into a full root mode, mostly because of this conference actually, just to see if it would work in complete full root mode. But we actually might go back to half root. And the reason for that is, so this is about a 1.5 month period where we're running in half root mode. This is when we decided to try a full Lustre root on all 1,500 nodes. These spikes you can ignore. They're just where we rebooted from one OS image to another, or when we were updating a kernel. So this is time on this axis. This is InfiniBand packets a second into the images metadata server. And half root mode, where you just put a couple of directories in the root of the file system in a RAM disk, has got about half the traffic of a full Lustre root mode. It's no big deal. The metadata server handles it, but things just run a little bit more slowly this way with the full Lustre root. You can also look at not just InfiniBand packets a second. You could look at load on the metadata server. You could look at bandwidth into the metadata server. All of the graphs look the same. Okay, so the pros and cons. The cons of root on Lustre. If the portal RPC daemon hangs for any reason, then your node is toast. We were actually worried about this when we started this, and wondered if network deadlocks were fundamental to, I mean, you have a root file system that's the other end of a network link. If your network struggles under any sort of virtual memory pressure, then your operating system can go away. And we really haven't seen it at all, except for this one case. So, you know, one user with one code running one sort of problem on one of our clusters, not a big cluster. So at the moment, we're inclined to completely ignore this and assume it's a kernel bug or a Lustre bug. And we don't think it's fundamental to this way of running root on Lustre. One thing that might be saving us slightly is we're using InfiniBand. And there's a lot of pre-allocated areas and not so many allocations in the InfiniBand stack compared to running root on Lustre over, say, GigE. So your mileage may vary. Another thing that I guess I should point out here is that we're very grateful to the CEA people and Lustre folks who keep rolling the Lustre versions forward, the client kernels that are supported as aggressively as possible. We've been running 2632 on all our machines as soon as we possibly could, and would love to upgrade to 2625, 2628 as soon as possible, because we have a feeling that problems like this would just be solved in a much newer kernel version. So the second point here is that really it's part of betting the farm on Lustre. If the thing that manages everything in the farm is the resource manager, your PBS or your Slurm, and if that hangs when root on Lustre goes away, or indeed hangs in a nasty way, if any file system goes away, then it can spuriously kill jobs. So the simplest thing to do here is just to put your PBS moms or equivalent on local disk or RAM disk, and potentially make other small modifications, and then they sail through any file system hanging. The last point here is really just a sort of, or just an example really of the fact that it works. The metadata server loads up. It takes some time to do. This time is just a representative time. The nodes are all very loaded. Doing one command on everything at once is pretty much the worst thing you can do to a root on Lustre file system. So the fact that it only takes 12 seconds on 1,500 nodes is I guess interesting, but it's not really important. The fact that it works is what's important. So the pros of root on Lustre, well, it really lived up to what we wanted. We wanted something that's manageable and simple. It's reliable as well. I thought about putting in a whole bunch of trying to characterize how its performance worked. But really loading an executable off a root on Lustre file system is no different to loading an executable off anything else. if you want to load up an MPI binary to run a 1,000 node job, it's the same as loading anything off Lustre for root on Lustre. All the stats are the same. So there's really nothing to say there. If Lustre works, root on Lustre will work. It does improve, and we're hoping it will improve further as Lustre improves, and it probably has already improved with all the read caches. So more of the OS being hot files are cached on the OSSs. If you want it to go a little bit faster, you can use this hacks like the half root thing where you put a little bit of the OS in a RAM disk. And you could also set up multiple images file systems, so multiple metadata servers and multiple images copies of the root file system on Lustre, and that would get you from 1,500 nodes to n times 1,500 nodes. The other thing is the last point here, we don't actually run in that mode at the moment. All of our file systems are distributed across all of our OSTs. But we have had some thoughts about dedicating a few OSSs to just running the operating system. And the idea there is that the working set of an operating system is really quite small. Something like 5 gig, 10 gig would do it, and that's trivially cacheable in the RAM on an OSS. So then you would have a complete RAM disk operating system living at the other end of a very fast fabric. And your only worry is that maybe with just a few OSSs you perhaps wouldn't have enough threads to handle peak loads. But it's worthwhile thinking about because it potentially is a little bit faster. And of course, being that it's always, all parts of the operating system are always client cached as well. So that's the end of the root on Lustre part of the talk. Metadata speed and how we manage to speed up metadata is another part of the talk. This is completely orthogonal to what was being talked about yesterday. Those are core Lustre, complex, detailed improvements. This is a very simple approach, and it's just OS tweaks, really. So the idea there being that, if Lustre improves their part of it, then it'll go faster. And it would add to all the speed that we gain through the tweaks we'll see later in this talk. So really, this part of the talk is covered in Lustre Discussed about 2 or 3 months ago. There was an interesting thread there that's badly named, and some of the people from that thread are here today. So I'm just really following that through and showing that it works in production and explaining why it works. So what's the problem? I guess everybody's seen very slow ls-Ls. It's a common problem. We eventually listened to our users and eventually believed them. And we measured some stats about our file system. And it turns out that big recursive LSs, or indeed any sort of LS in a big directory, runs about 100 files a second. This is a little bit extreme. Of course, the second time you do this, it runs at about 30 plus thousand files a second because it's all cached in the client. But if you come back the next day, do the same thing again, it again runs at about 100 files a second. So the second point here is that it's a bit ridiculous when our attempt at a daily backup takes more than 24 hours. So it's a metadata problem, right? So we go look at the metadata server. Turns out that's not the problem at all. All our metadata server loads are very low, they never hit hard. All of our file system data fits entirely in the RAM on a metadata server. So the corollary here is that all our MDTs after a while are 4K write-only media and sort of intrinsically not suited to SSDs. So we can also measure that the MDSs aren't the problem. So on a test cluster which had really quiet OSSs, so we're basically taking the OSSs out of the picture, you can drop all the MDS caches. So you drop everything it knows about inodes and D entries and everything else out of RAM. And then you do a file system sweep again, and it only slows down by about a factor of 2. So doing whatever you like on the metadata server without actually changing Lustre code won't change your speed by more than about a factor of 2. So it turns out that the problem is on the OSSs. We've got very busy OSSs. We stream a couple of gigabytes a second, read and write 24/7 through all of our OSS caches, and we have about a terabyte of OSS cache. So assuming we get some cache reuse, we're still going to blow it away in about 10 minutes, maybe 20 minutes. So it turns out that if you stream lots of big data through the read and write through caches in Lustre, it pushes all of the LDISC-FS inodes for your OSTs out of RAM. So that means that every time you go and do an LS, it has to go and try and read those again off disk. So of course this causes an awful lot of seeks on the disk. Every time you do an LS, you have to start doing a whole lot of seeks again. And this probably impacts streaming performance a little bit as well, but it mainly just impacts metadata performance. So you can actually see this interactively. If you fire up to Windows, log into an OSS, run slab top, and you can see the inode and de-entry caches go up and down as you do a large LS. As pretty much as soon as you finish, and even whilst it's going, you can see all the inodes and de-entries being dropped again straight away. Because all of the data, the big data that's coming into the read and write through caches is pushing those out of RAM. So there is a solution, and some people run this way. You can just turn off the read and write through caches. Then you won't have a metadata slowdown. However, just a quick look at the stats for our big file system says that we actually get quite good cache hits using the Lustre page caches. So we really don't want to do this. And of course, there's cases where you've got a small input file that's read by 500 threads, and you only read it from disk once, spread it out to the 500 threads. That's a clear win for OSS caches. So we really don't want to turn it off. So in this thread on Lustre Discuss, Kit Westneat suggested we have a look at VFS Cash Pressure. And we thought that was a very good idea, and we ran through it. We ran with it, and that's what I'll talk about in the rest of the talk. So it's possible that something like size on metadata might help this too, because if you don't have to go to the OSSs for any metadata at all, then it solves this problem as well. So this could be a temporary problem, a temporary fix until size on metadata works. So it turns out we're already looking at VFS Cash Pressure from another point of view. So we have file system scanning nodes, and on those nodes we tended to get too many inodes and de-entries cached, and that was causing out-of-memory problems on the clients. So we're actually setting VFS Cash Pressure to a very high number on our file system scanning clients, and Kit's suggestion was to do the opposite on our OSSs, set VFS Cash Pressure to be a very low number to try and cache a lot of OSS inodes. So what is VFS Cash Pressure? It's a simple operating system setting. It's the balance between how many times you scan looking for pages that can be freed versus how many times you scan looking for inodes and de-entries, slab information to free. It's 100 by default. If you set VFS Cash Pressure to be 0, that means you never, ever, ever reclaim any inodes and de-entries. So this is a scary thing to do. But it turns out that inodes and de-entries are tiny, really tiny. So if you have even a reasonable amount of memory on your OSSs, you can cache an awful lot of files. So 1 gig of RAM on one OSS can cache about 1 million inodes and de-entries. If you don't have a lot of RAM on your OSSs, you probably shouldn't be running with read and write through caches at all, because you just won't get very many cache hits anyway. This is really only a setting that applies for people with large memory OSSs. So the other point is that if we set it to 0 or a very low number, and we never reclaim any inodes de-entries, then as our file system size naturally grows, we get more files. We can OOM our OSS that way as well. But it turns out that inode growth is actually really slow on our file system anyway, and it's not a problem to just monitor this every week or every month. So I did some more testing on a test cluster with an artificial I/O load, and unfortunately it showed that any value of VFS Cash Pressure other than 0 really doesn't help. So I think this is because when you do large stats, data head kicks in, it's statting lots of files at once. If any one of those is slow, then your whole LS goes slow. So you basically have to set it to be 0, and you have to really bite the bullet and do the sums and set VFS Cash Pressure 0. So we do that, and we're very happy. It works. It's kind of spectacular. So we sort of measured speed ups of 20 to 40 times on a recursive LS of just a few 100,000 files in a known directory that never changed. And our async backups went from a time of about something more than 30 hours to about 3 hours. So this speed up here is actually completely dependent on how loaded your OSSs are. You might only see a small speed up. I've seen 60 times speed up, going from 13 minutes to 13 seconds. So now we've gone from about 100 files a second on a typical uncached client to about 4,000 stats a second. And again, when it's fully client cached, it goes up to 32 again. But the best thing about that is it's repeatable day to day. So you can come back the next day, do the same LS in the same directory, and it still runs at about 4,000 files a second. So problem solved. Except it's not. Turns out if you create 100,000 files and delete them, the inode count goes up by 100,000 and drops. D entries go up by 100,000 and stay there. So I don't know why this is, but it appears that D entries are only ever reclaimed by VM pressure in this operating system. So for example, we've got about 30 million files total, and we have about 200 million D entries. So these OSSs have been running for a couple of months, and we've accumulated a lot of D entries. But this kind of sounds scary, but the only real effect that we can see is that we're using a little bit more RAM. So we have a total of 23 gigabytes of cached inodes across all our OSSs now. We have 39 gigabytes of D entries, but we have a terabyte of RAM on our OSSs. So this is a negligible part of the RAM. And really 95% of the RAM is still dedicated to OSS read and write through caches. So we quite like to solve this decache, this D-entry problem. And we use the big hammer that we have available. We hack the kernel. And so I created a VFS Cash Pressure setting of 100. And it doesn't work. Of course it doesn't work. If you have to go seek at all across the disks, looking for all this small data, it'll make everything go slow again. So that was a waste of time. So the only practical solution that we've found is to set VFS Cash Pressure 0 on all our OSSs and run that way. And then occasionally, a day, a month perhaps, you set this to be greater than 0, let the D entries and inodes reclaim under memory pressure, and then you set it back to 0 and you live with slow metadata speeds for a day or so until all the caches on the OSSs repopulate. So that's the end of my talk. I'll just give a quick summary of both parts of the talk. So root on Lustre works very well for us, ticks all the boxes as far as we're concerned, but it is a bit of work to set up, and this is the wiki page for it. And I actually hope to get a lot of these, or some of these changes a little bit generalized and push back into one sys, so it'll be easier for other people. Metadata. It's a common problem that metadata is slow. We narrowed it down in our particular case to very busy OSS read and write through caches, pushing inodes and D entries out of RAM. With some forethought, we carefully set VFS Cash Pressure 0, and that fixed the problem, and everybody's happy. Thank you.
Questions for Robin? I figured.
I'm in trouble now.
No, nothing. Have you tried the read cache max file size to say only cache small files, so that the page cache pressure doesn't cause the kernel to evict the data?
So yeah, you could set a maximum file size, but if you had enough files of that size or less, the cache would still fill up. You'd still got memory pressure, and you still got inodes and D entries being dropped. So I think it might help, but it wouldn't actually solve the problem. We haven't tried it.
Hi, we have a testing environment that do node provisioning for our testing environment. And we have been using NFS diskless root, and we have done experiment of using Lustre as the root file system about 1 year ago. but according to Lustre's implementation design, it's not designed for used as the little small I/O, such as the operating system files. And so I'm wondering, what's the performance if there are many nodes in your environment? If there are many nodes, such as 100 nodes that are accessing the same root file system that is based on Lustre, and do you have significant latencies that the user can experience?
The only time, we have 1,500 nodes on root on Lustre, and the only time we experience anything more than any observable delay that the user might see is when we're running a full check script that checks the node health across every node, which we run a few times a day. And when we just do a CExec or a PDSH to every one of those 1,500 nodes and do the same thing at the same time, then locks on the images metadata server cause a lot of load on the images metadata server, and a user hitting return on a login node would experience about a 1 second delay, and that goes away as soon as they've finished. And we didn't actually see this in half root mode, so I suspect that, don't know if I mentioned it when I was looking at that graph, but I suspect just having the root inode itself in a RAM disk is enough to get around that problem. Because every file access on the system goes and stats root as part of finding a path to a file system. And by setting full root on Lustre, we're forcing every file system access to every one of our other file systems, so the bigger file systems, not images. We're forcing that to first stat images and then go to that file system. So it's like a 2 round trips. It's probably not ideal.
Okay. Another question is whether many nodes share one root system or they have their own one. Whether each node has its own root file system.
Each node has got they all share one root file system. So it's a read-only root file system. One sets up a set of tiny symlinks that differentiate each node from each other and set up different services on the login nodes and on the data mover nodes. It's one root file system. There's no reason why you couldn't copy that 20 times on Lustre and have some sort of a round-robin system so they all hit different root file systems, but it's actually better just to have one because that's cached in the OSS read caches a lot more effectively if you just have one set of inodes and one set of operating system data that's cached in your OSSs.
So you need to first mount the Lustre root as read-only, and then how do you handle the modification of same files across different nodes?
OneSys handles that for us. OneSys is a provisioning system that handles that for us. It sets up a little RAM disk and it's got a bunch of symlinks that point back to the read-only image. It's really, it can be used for other things, but it's commonly used for read-only root file systems.
Okay, and then how do you keep the changes after node rebooting?
How do we keep, sorry?
After the node reboots again.
There's no state. There's no state on the nodes apart from what we need to keep the PBS moms happy on the nodes. Then there's no state at all. All our nodes are completely interchangeable.
Okay, good. Thank you.
I've got a question. So you went from 30 hours to 3 in terms of your rsync. Maybe you said this, but how large is that rsync?
I really don't know. Our home, we only back up the home file system, which is quite small.
Okay.
I don't know. I'd guess a couple of million inodes, something like that.
Okay, groovy. Sorry?
On home, no, it shouldn't be 20 million on home.
20 million?
No
right
way.
on.
Hey, all right, thanks.
All right. Thanks a lot, Robin.